Hello everyone. In this video we're going to discuss partial derivatives for functions of two variables or more. We've seen already in our work what the partial derivatives are and how to compute them, and geometrically for a function of two variables the partial derivatives represent the slope of the graph of the function, the slope of the surface, in the direction of increasing x or increasing y respectively. Another question we're going to ask and answer with directional derivatives is how can we determine the slope to the graph of a function of two variables to the surface z equals f of xy at a fixed point on the graph in any specified direction. Alright, so how are we going to do that? Well, what we're going to do is we're going to try to find a curve on the surface at the point that passes through the appropriate point and points in the appropriate direction, and we're going to define what that means. Then we can define the slope of the surface to be the slope of the tangent line to that curve at the given point on the graph. Now let's look at this geometrically before we get into the details, which are quite vast, but let's go over and take a look at Paul Seeberger's applet. So this is from my colleague Paul Seeberger at Monroe Community College. If you Google this CalcPlot 3D Java applet, it should come right up. Now what we're going to do is just leave the initial stock function that he has in here. We're going to click on the third keypad over to the right there. When we do that, we're going to notice a little drop down menu appears. I'm actually going to first turn the edges off on the graph, and then in the drop down we have multiple options. We can show the gradient vector, we can show the trace, we can show lots of different things on here. I want to show the directional derivative trace. Alright, and something's going to change with the graph. Notice the graph became a little bit transparent, and what we can do is now select any point we want just by clicking into this box here, or you could specify the ordered pair by actually typing it in. So maybe I'll just change this to 1, 1, x equals 1, y equals 1. Alright, now over in the graph what we're seeing is a couple of things. There's a curve which is on the graph of the function. The black segment there is the tangent line, and down below you see this green vector that is lining up with this vector here, and we want to think about that as our direction vector, and we can use this slider over here underneath to change that direction, or we could just specifically type in a specific direction like 155 degrees for instance, and then it'll change it there. Notice when we move this slider that we're seeing this green vector change. Okay, the curve's obviously changing over there, but we're going to want to think about that direction vector as like our compass. If you're thinking about doing some hiking and you have a compass and you're pointing it in the direction of what you're going to walk, that's what the green vector is signifying for us in the applet here. Now let's just specify so we're at the point 1, 1. Notice when we move this around, it changes the direction of that vector. Okay, and we can see in the picture here it makes a big difference on the slope, which is the slope of this tangent line. If we're pointing in the green direction, in the direction of the green vector down on the xy plane, then we're going to be going down this curve, and therefore our slope will be negative. Alright, our rate of change is going to be negative. That's what we're going to call the directional derivative. If we wanted to go opposite that, say we wanted to go over into the third quadrant, or maybe like 225 degrees, so let's change this to 225. Then notice the green vector is now pointing this direction. Over here in the xy plane we're seeing it point there. Now what we're saying is we're going from this point 1, 1 on 1, 1, whatever the z coordinate is, 0.94 as we're seeing at the top of the screen, we're going to go up this curve. So they're moving in that direction, okay, from the point on that graph right there, the blue point, we're going to be going uphill. Our slope of the surface will be positive there. Alright, so that's the idea geometrically what we're going to try to compute. We're going to try to define that and then show how to compute those. Okay, so going back to some of the specifics here, we've seen, and even just looking at Seeberger's applet, about the trace curves. So in our prior work in dealing with limits in partial derivatives and the chain rule, we have always, to get a good visual for this, taken a curve, little r of t in the xy plane, and feed it into the function to generate what we've called capital R of t, which is the corresponding image curve on the graph. All right, so the x component is x of t, the y component is y of t, and the z component is f of r of t, what you get by plugging in x of t and y of t into the function f. And we can have some pictures related to that there. The curves don't have to be straight lines. They can be. They can have some curve, some bend to them. The third component of that curve capital R gives us the z component, obviously, but that represents the height on the graph. That's just an important note to make relative to the xy plane, relative to the z-axis. Again, z of t is f of r of t. It's the height on the graph. Now, how do we determine the direction that we're moving in? The curve down in the xy plane, the red curve here, determines how we're going to travel on its image on the surface. So that kind of dictates which direction that we're moving in, and it's going to do so through its derivative. So we're talking about the curve little r of t in the xy plane and its derivative vector. Now, assuming that we have the derivative, we have the point that the vector, pardon me, is passing through the point AB. That's the point we want to focus on, and for convenience we're going to assume that's happening when t is equal to 0. Then the vector v, which we're going to call the vector v is defining to be the derivative at 0, that's going to dictate the direction that we're moving in, okay, at the point we want to focus on the graph of the function, which is this point here. What we get by plugging t equals 0 into the function capital R to get to the point a, b, and then f of a, b. In general, the derivative vector is the direction to the curve capital R of t, all right, at the instant of time you're talking about. We can think about that r prime vector, little r prime, as the compass direction vector in the xy plane. Going back over to Seeberger's applet, again, that compass direction was given by this green vector. When we change that, it definitely changes the direction that we're moving in, and therefore it's going to change the slope. Okay, continuing on. Given the curve r of t, all right, with its derivative, and knowing that r of 0 is equal to ab and its derivative at 0 is v, we're going to define the slope of the surface at the point we're questioning to be the slope of that tangent line. Okay, so how do we compute that? That's what we want to know. All right, so remember from calculus that the derivative represented the slope of the tangent line. We've seen here in calculus 3 that we can actually take any ordinary calculus 1 function and parameterize it as a vector valued function, and what we would know from this then is that the derivative of that last component would be the slope of the tangent line. Alright, so just taking the derivative component by component, we would get that the derivative of that last component is the slope of the tangent line. So that's the question for us now. Is the same thing going to happen here for us? Meaning, if we look at the function we've been talking about, capital R of t here, all right, where the third component, z of t, I'm just underlining it here, is equal to f of r of t. It's the height on the graph, all right, just like little f of t was in the for the calculus 1 scalar valued function. Will that derivative give us the slope we're looking for? That's our question right now. That is the main question we're going to ask. Can we just differentiate that third component? Will it give us the slope that we want? Well, we know how to compute that by the chain rule. All right, the chain rule tells us that the derivative of this composition, this is why this is one of the most important applications of the chain rule, is equal to the derivative of the outside function, which is the gradient, dotted with the inside function. I'm just writing the derivative in a couple of different ways here and here, dr dt or r prime. In the last equals there, we're just emphasizing that it's really the gradient of f at r of t, all right, evaluated at r of t and then dotted with r prime of t. So there's a dependence on t there, which we might sometimes suppress. The question now becomes then, because this right here is our derivative, okay, this is equal to z prime, is that derivative the slope of the surface? All right, so that's what we're going to figure out next. Okay, so to do that, we're going to do a little bit of looking at the vector derivative capital the derivative of the vector valued function capital R. All right, so remember, capital R of t was the three-space curve x of t, y of t, and then the third component was z of t, which was f of r of t. What we get by taking the function and restricting it to that curve. We're calling that simultaneously z of t. Now, we know how to compute that derivative of that vector valued function. You just differentiate component by component. By the chain rule, the derivative of the third component is the gradient dotted with r prime. Now, what we're going to do is to see if that derivative of the third component is equal to the slope we're looking for, we're going to decompose that vector capital R prime into two pieces. One of them is going to be parallel to the xy plane, and the other one is going to be parallel to the z-axis. And we do that just by splitting it up. All right, just by adding these two vectors together, by essentially splitting it into these two pieces here. All right, notice the third component of the first vector is 0, whereas the first component and the second component of the second vector are both 0. Adding them together, we would get back where we started from. But by doing that, we can realize that this vector here is actually parallel to the xy plane. You can think about it living in the xy plane. Yes, it has a third component of 0, but just projecting that down on the xy plane, we can view that as a vector in the xy plane. And moreover, the last vector we have here is a scalar multiple of the vector k, the unit vector k, and therefore it is a vertical vector. All right, let's look at some pictures we've got here below at this decomposition. So the red vector, which is tangent to the graph, all right, is this capital R prime, or capital dr dt. We are decomposing that as a sum of two. One, which is a vector parallel to the xy plane, that's the derivative of little r. One, which is a scalar multiple of k, right? It's the vertical vector. This one is just saying we're moving in this direction. And again, we have the derivative and then the vertical vector, the derivative of little r and then the derivative vector. That three-space vector, the red one, is a sum of those two. Now, we know how to compute those slopes. All right, the slope, all right, of this line containing that vector will just be the rise over the run. The rise over the run, including the sine of the rise, is just going to be, as we're picturing here, the length of the rise, which is that scalar multiple of the vector k, divided by the run. Well, the run, we're going to have to take the magnitude of that vector. So let's go back to that picture just for a moment. Again, what is this standing for? This part of right here only will be the rise. And the length of this vector, so the length of dr dt, or little r, derivative of little r, that is going to equal the run. All right, so we want that length, the ratio of those two lengths. All right, the rise over the run. And then I've just wrote that right down here. All right, and then at the end here, just replaced the dr dt notation for the r prime notation. So again, we could think about the numerator as z prime. What we're going to say then is the derivative of that third component, well, that will equal the slope. Well, that's the slope right there. If we want this to equal z prime of t, then we need this numerator to be equal to 1. And that's the conclusion that we're making here. All right, so we get that conclusion, that the derivative of the height function will give us the slope we're looking for only if the length of the first derivative is equal to 1. And that, as we've learned in Unit 2, will be true as long as the curve little r of t is parameterized by arc length. Okay, so again, just to reiterate, the derivative of that third component, which is the derivative of the height function, will give us the slope of the surface pointing in the direction dictated by the curve little r of t only if the curve is parameterized by arc length. In the next video, we'll say how to define a directional derivative using this fact.